Hey, I'm Sofia, and this is a summary of Component 1. Our research question was, how does the increase in global temperature affect the number of major hurricanes in Florida? Our 5 open research questions were, what factors contribute to the formation of hurricanes? Why is Florida specifically prone to hurricanes? Is the relationship between temperature and hurricanes directly proportional? When did global temperatures start to rise? And how is the intensity of hurricanes related to global warming? Here's our rationale. Hurricanes are one of the most devastating natural disasters Earth experiences. These tropical cyclones impact thousands of lives each year. We decided to explore this topic because climate change and hurricanes are huge problems the world faces. Climate change affects everyone. As per our extensive literature review, we learned a lot of things throughout this process. We learned what the ingredients for a hurricane are, which are, quote, a pre-existing weather disturbance, warm ocean waters, high humidity, and light winds high in the atmosphere, end quote. That quote is from an article called Earth's Forecast, Hurricanes and Climate Change by the Florida Museum. That article also taught us that hurricanes are intensifying. We also learned what the definition of a major hurricane is. A major hurricane is, quote, a hurricane which reaches Category 3, sustained winds greater than 110 miles per hour, on the Saffir-Simpson hurricane scale, end quote. That quote was from Hurricanes, an article, by Florida Climate Center. Let's take a look at our results in the form of graphs. This first graph here shows the number of major hurricanes per decade. And as you can see, there's not a lot of clear exponential growth here. The second graph takes a look at the increase in global temperature throughout time. And as you can see here, there is an increase, and it could possibly be made into an exponential equation. And as for our final graph, the one which combines both of those last ones, we plotted the points and we did the research, but there is not a clear exponential correlation here. However, the temperature versus time graph shows correlation. So in this video, we are going to be examining this graph and applying our findings to hurricanes. So without further ado, let's move on.
I started by looking at the first interval. So our data started at 1880. So I said that the year 1880 would be x equals 0. From there, I just took the temperature, which we found to be 56.71 in our data. And so I decided that that had to be 8 because at that point, right, applying the exponent of 0 for the interval means that the entire rate would be 1. So at that point, a would be equal to the y value for x equals 0, which is 56.71. From there, I just looked at the different intervals that we had recorded in our data. I started with x is equal to 12, or the 2000s, and I used the temperature that we had calculated from there to find the rate according to the exponential growth formula that we used in class. I did this a couple times. I used also the 11th interval for x equals 11, or the 1990s, and the 10th interval with x equals 10, or the 1980s for our time period. And then from there, I just plugged in all of our data points basically as they were into Desmos, and I applied the various equations I had found. And then I decided which of the equations hit the most data points that were graphed. And that turned out to be the equation I found for the interval x equals 10. That was f of x is equal to 56.71 times 1 plus 0.00141922 raised to the power of x. I calculated the average rate of change for the 1990s to the 2000s. So 1990, I decided what we said was x equals to 11, and 2000 was x equals to 12. So I used our formula that we derived earlier. F of x is equal to 56.71 times 1 plus 0.00141922 raised to the power of x. From there, I used the regular AROC formula. I put f of 12 minus f of 1 over 12 minus 1. I did the calculations, as you can see here, and I found that my answer was 0.08174945. And I believe that's just the rate of change for that specific interval, showing that the rate of change increased over time, showing that the rate of temperature increase also increased over time, which makes sense in the context of what we know about climate change, and that things have progressively gotten worse because the amount of carbon that's emitted into the atmosphere has gotten higher and higher as things like more cars are being driven, more factories are producing things, and just generally there's not enough work being done to mitigate the effects of a larger population inputting to climate change.
Hello again, it's Sophie with another average rate of change problem for you. Let's look at 1910s and 1920s, where x is equal to 3 and x is equal to 4. We use function notation to get the equation f of 4 minus f of 3 divided by 4 minus 3. In order to find f of 4, you take 4 and you substitute that for x in the equation that Sarah came up with to get 57.033. And you do that with f of 3 to get 56.952. Take those two numbers and put that back into the function notation equation to get your answer as approximately 0.081. That number means that for each decade, the temperature increase in Fahrenheit is 0.081. That may not seem like a big number, but throughout time, that is a huge number. But now let's apply that to Florida hurricanes. So, in the years 1910s and 1920s, you can see that there is an increase in hurricanes. So, that hints at a possible correlation between the increase in global temperature and hurricanes in Florida.
Alright, so I calculated the average rate of change, or AROC, for the years 1880 to 1890, meaning the variables f of 0 and f of 1 respectively. I used the line of best fit we calculated earlier to find the values and proceeded to plug it into the standard AROC formula, f of 0 minus f of 1 over 0 minus 1. The answer I got was 0.080802, which would be the average change in temperature that decade.
So I calculated the instantaneous rate of change for the 1930s, or x equals to 5. I used our already pre-existing f of x equation, and I worked through the math as you can see here. And I ended up with a rate of 0.08099. And so what that means, right, is that the temperature increased by a rate of 0.08099 for that time period, for the entire 1930s. I thought this number kind of seems to make a bit of sense, right? It's less than the numbers we see for average rate of change and instantaneous rate of change later in time, because, right, the effects get worse over time and there's more people and more things that contribute to climate change. But the number's also not so low as it would have been, say, pre-industrial revolution, pre-war efforts, things of that nature, which inputted more to climate change as more factories had to produce things for the war effort, and just generally there were more people contributing to climate change than there had been previous.
Wait, what time is it? Oh, I know. It's time for some more instantaneous rate of change. All right, let's look at 1990, where x is equal to 11. We have the equation f of 11 minus f of 10.999 divided by 11 minus 10.999. What's f of 11? Well, all you have to do is take 11 and input it into the equation that Sarah came up with earlier, and you get your answer as 57.601633. And as for f of 10.999, the answer is 57.6015517. So now we input those values back into our function notation equation, and we get our answer as approximately 0.08169. What does that mean in terms of the problem? Well, that means that at that given point, the temperature was increasing 0.08169 degrees Fahrenheit per decade, which is, again, kind of a pretty big deal, you know? That's a lot in the grand scheme of things. That is a huge temperature increase. And as for hurricanes, let's take a look at that graph. If you look at 1990 in this graph, you'll see that it is increasing. The amount of hurricanes are increasing, which does correlate to what we just discussed about the 0.08169 increase. So there is correlation here ever so slightly.
I calculated for the instantaneous rate of change, or IROC, for the year 1890, or f of 1. I plugged f of 1 into our line of best fit equation, as well as the variable f of 0.999. After plugging these values into the standard IROC formula, I got 0.08054, meaning the temperature changed by that value for the decade 1890. I calculated for future predictions 20 years in the future, 50 years in the future, and 100 years in the future. First off, we need to find the values of x in those years. As x is the number of decades since the year 1880, you just need to perform some simple math to find f of 16, f of 19, and f of 24. By plugging those values into our line of best fit equation, I predicted by the 2040s the global temperature should be 58.0115452 degrees. By the 2070s, it should be 58.258888682, and by the 2120s, it should be 58.67347311. We see the further into the future we get, the higher the global temperature gets. This makes sense as global carbon emissions have been on the rise as population grows and industrialization spreads. Looking at global politicians, there may be efforts in further preventing global warming, but only time can tell.
Alright, so to calculate what would happen if we were to double our outcome, I started by finding the y value for f of 12. And I found that to be 57.68338288. I then took this number and I multiplied it by 2. I plugged that number back into our equation for the line of best fit and worked backwards to solve for x. I found that to be x equals 500.7462411, which I rounded to about x equals 500 because I knew that would be taking place within the 500th interval of our data. So that means that 500th interval would be 5,000 years after 1880, which would be 6880. So this doubling outcome would occur in 6880, right? And because this temperature doubled, you can see it's a much larger temperature than we started with, which means the amount of hurricanes that would happen is likely to be extremely large. However, according to National Geographic, the Earth's ice actually starts melting once the Earth reaches an average global temperature of about 80 degrees. So at that point, all of the ice of the Earth would already be melted, which would create more water and make the sea levels rise, which would create even more hurricanes than the heat would already cause. Somewhat fortunately, however, it is likely that humans will be extinct by that point, so it's not really something that humans are going to have to worry about. For the tripling calculations, I followed the same process. I just tripled my f of 12 value rather than doubled, and then did the same thing to work backwards, and I found my value to be x equals 786.644464, which I again rounded to x equals 786, which I found would happen in about the year 9740. I apologize. And of course, these numbers are not exact, but even if you were to work with the exact data that we have for the 12th interval, then the temperature would actually be even higher, which means there would be even more hurricanes. But once again, this likely won't be a large issue for us, at least, as humans likely will not be living on the planet anymore.
All three AROCs and IROCs we found increased as the years went by, which is scary because of the detrimental effects an increased temperature has on the planet. In 20 years, the global temperature will approximately be 58.01 degrees. And in 50 years, 58.26 degrees. And in 100 years, 58.67 degrees. All those were in Fahrenheit. Doubling size occurs in 6,880. Tripling size occurs in 9,740. The increased global temperature warms the ocean waters, which is a key ingredient for hurricanes. A higher temperature means more Florida hurricanes. It's important to shed light on climate change because it affects everyone. We have to live life in a more sustainable manner. I hope you have a great day and appreciate the world we live in. Bye.